Now let's study about the MRI. MRI is magnetic resonance imaging. MRI is related to NMR. Then, what is NMR? NMR is nuclear magnetic resonance. I'm sure you're quite familiar with the NMR. Organic molecules are mainly composed of carbon and hydrogen. And to figure out the structure of organic molecule, distinguishing different carbon and hydrogen atoms are important. This is one of the earliest proton NMR spectrum obtained for organic molecules. The molecule is ethanol, and this spectrum was taken in 1951. Looks like quite poor quality, isn't it? But this was the scientific turning point to show the possibility of distinguishing different hydrogen atoms in spectroscopy. This ethanol NMR shows the different environment around each different hydrogen nucleus. Of course, in modern days, we can get much better NMR spectrum with lots of information, including chemical shift and coupling constants. As the NMR is so powerful to analyze the organic molecules, even some people say, after NMR is developed, no more research. That's another abbreviation of NMR. With this great potential, multiple Nobel Prizes were awarded to NMR techniques during the last half a century. MRI is magnetic resonance imaging. In principle, NMR and MRI, they are exactly the same technique, but the word of nuclear reminds people radioactivity, so in medical field, MRI becomes the standard term. But in reality, NMR has nothing to do with radioactivity. At least the word imaging in MRI implies the display of the data is not spectrum, but imaging. This is one example of MRI images. First of all, you can realize that this is the tomographic image, right? This is a sectional image, but made by CT. Comparing to X-ray CT, what is the biggest difference here? Well, X-ray CT shows you only bones, but in MRI, we can see the soft organs such as the brain. In X-ray, if a bone was the contrast agent, what is the contrast agent in MRI? It is hydrogen. Then, what is the most abundant source of hydrogen in our body? That should be water. So, most of the MRI images rely on water in the body. It's quite convenient. The different contrast in the image is due to the different environment of water molecule in the body. Let's think about the mechanism of MRI. Hydrogen nucleus has a spinning effect. If a charged particle spins, it behaves like a small magnet. So we can say we have many small magnets in our body, but they may be oriented randomly. If you apply strong magnetic field from outside, the magnets can align. Then we can say our body is magnetized. As the nuclear magnets are not static and quantized, the direction can be either up or down. Depending on the directions, under a strong magnetic field, there can be two populations of magnets. If they are different in energy level, by applying electromagnetic wave, we can excite the lower energy magnet into higher energy level. This is quite similar to excitation of an electron from lower energy to higher energy level. What range of light did we use for the electronic transition? Do you remember? It was either in UV or visible light range. Nuclear spinning is much slower, and also the energy gap is quite small. The required energy for this transition is microwave, which has a much longer wavelength than visible or even infrared light. This range of electromagnetic wave is in megahertz range, which may be familiar with you as 300 or 500 megahertz animal. If electrons are not paired, they also behave like a magnet with a spinning effect. Then Similar type of energy absorption is possible in magnetic field. The energy level is in gigahertz range, which is much higher than NMR. And this ESR, electron spin resonance technique, is very useful to check whether the molecule has a radical in it. After excitation, if the irradiation of radio frequency is stopped, the excited state nuclei can be relaxed, releasing the electromagnetic wave. The different energy gap for these two states for different hydrogen is the basis of chemical shift in NMR. In MRI, more things we need to consider. As each magnet spins this way under external magnetic field, the magnetized vector has a G and XY component. Before excitation, the XY components are averaged as 0 due to the random phase. Only pure G component exists before excitation. When excitation occurs, the XY component is synchronized to make XY vector, and G component is decreased. When activation is stopped, each component will come back to the original position through so-called relaxation process. During this relaxation process, it is possible to isolate out the G component from XY component. The G component change we call T1 relaxation, and XY component change is a T2 relaxation. It may be easier to see a movie clip to understand this excitation and relaxation process. In the beginning, the spin vector is facing upward. When activated, the vector is moved down to 90 degrees, then G component is decreased, but XY component is maximized. Then, slowly it comes back to the original status. Here we can get the G component change by T1 relaxation. If you look at the relaxation from the top view, in the beginning, the XY component is synchronized with the maximized XY vector in yellow color. Over the relaxation, XY components are randomized, the vector sum is reduced, and the change can be monitored in terms of T2 relaxation. T2 relaxation is much faster than T1. The randomized XY effect can be easily separated from G component changes. Could you get a good idea for the T1 and T2 relaxation? I hope so. Let's start with the T2 for brain imaging. In the middle of the brain, there is an area so-called cerebral spinal fluid, CSF area, which is filled with fluid. Usually the relaxation is faster in rigid solid part than soft liquid part of the tissue. T2 is measuring the XY component, so the starting point has a maximum value and decreases slowly. Solid part of white and gray matter has a fast relaxation than CSF area, so if you observe T2 at this time point, CSF has a higher value, so brighter images we can get. You can choose different time point for best image or information. Among these three images, seems like the middle one, 90 millisecond image, seems like the best for the contrast. Among MRI imaging probes, ion magnetic nanoparticles were found to accelerate the T2 process. If you add T2 accelerating probe, what do you expect? Brighter or darker image? Remember, for T2 imaging, faster relaxation gives you darker image. Upper image here is a normal brain. Lower image is magnetic nanoparticle treated brain image. And this area shows the darker contrast than other background. That means this area has accumulated magnetic nanoparticles. Now let's move to the T1 image. T1 is for G component, which is the smallest at the excited state and get recovered during the relaxation. So the signal increases over the relaxation time. The relative relaxation trend is similar to T2. Rigid part is faster for the relaxation. If you observe at this time point, CSF is darker than gray matter or white matter. T2 has a CSF as brighter, Do you remember? Then, by looking at this relative contrast, we can tell this image is a T1 image as an opposite contrast of T2. In T1, also you can select different time point for the best contrast. You have seen both T1 and T2 images. Which one gave you a better anatomical contrast? Usually T2 is better for the contrast and more popularly used for anatomical structure. Now let's think about the contrast agent application. In MRI, imaging probes usually called as a contrast agent. And all the contrast agents accelerate the relaxation, either T1 or T2. Let's say here is an untreated brain MRI images. When you treat with a contrast agent, if it shows you brighter contrast, as here, is this T1 or T2 agent? If it is a T2, the image of the contrast agent was darker, you remember? So this should be T1 contrast agent. The popular T1 contrast agent is either manganese or the gadolinium. Let's summarize. MRI contrast agents accelerate the relaxation. T1 agents are paramagnetic atoms such as gadolinium or manganese, which gives you brighter signals. T2 agents are superparamagnetic or ferromagnetic atoms such as iron and gives you darker contrast images. Considering these contrast agents, can you think any naturally occurring contrast agents for MRI? How about the hemoglobin? They have ion metals in heme center. And there are two states, oxygenated and deoxygenated state of heme. Among them, oxygenated area is functionally more active, and this difference could be imaged by photoacoustic technique too. Among those two, deoxygenated heme is ferromagnetic, and they can be good T2 contrast agent. As the contrast can tell the functional status of the tissue, this can be called as a functional MRI. Or it is called BOLD, blood oxygen level dependent MRI. In animal model, by changing the oxygenation status, we can get different BOLD image. From top to bottom, the oxygen concentration is decreased and the contrast becomes darker and darker. So this is one example of BOLD images. Can you tell whether this is a T1 or T2 images? This should be T2 images. The BOLD technique also can be used for mapping of a brain for the functionally active area. When visually activated, some area becomes brighter, which means functionally more active with higher oxygen concentrations. As you can see the time resolution here, the change can be monitored in second range. The same technique can be used for different functions such as sound response or the speech functions, which is quite similar to FDG PET experimental data. The advantage here is you don't need to use radioactive compounds. Previously we have seen PET is a good molecular imaging technique, but their spatial resolution is not so good. While PET X-ray CT has been used for overcoming the anatomical mapping, now MRI can take over to give better information for the soft tissue part. Due to the technical difficulties with the requirement of a high magnetic field in MRI, this is a cutting-edge new technique being introduced to scientific field. So far, I tried to introduce you the currently available clinically applicable imaging techniques. While a lot of development has been made, more specific and safer molecular imaging probes are always needed for better diagnosis and therapeutic monitoring. And this is the end of the class. Now, as usual, you can put up your questions to IBLE, then we can discuss together in the next week class. Have a good week and see you next week.